Good day, ladies and gentlemen. You're all very welcome to this Saturday's technical session of the CNPS. Today, we're delighted to have Jeff Baugher here to address us. I understand he has addressed ourselves, or maybe the preceding organization, NPA, some years ago. But we have been in touch with him through Nick Percival, actually, and it was thought opportune to invite him to give a presentation. Actually, he might explain this in detail himself, but he's in the process of producing a very detailed technical paper on this. And there are problems about, if he gave us all the details now, he might be breaking copyright. So we've persuaded him anyway, and he's very kindly acceded to agree to give the presentation today, having in mind that maybe not everything that will be in the paper, the forthcoming paper, will be out. But the whole question of dark energy is something that we have addressed in preceding weeks, and in particular we run these cosmological sessions under Harry Ricker, and this has been a bone of contention. So Jeff's point is that we know dark energy is sort of integrated with the modern ideas of general relativity. And he's just crudely saying, is general relativity inside out? Is it just completely wrong? And so we're considering the important aspect of dark energy, which is all pervasive in the context of general relativity. As usual, I think we have everything working. Jeff has slides, very detailed slides, because I've had a preview of them. And he's going to project them and talk to them, and as usual, we'll have maybe an hour, maybe a little, maybe a good bit more than an hour, actually, because it's a complex subject, and I know Jeff is quite mathematical on some of these. Although we try not to frighten you too much, I'm sure. And then we'll have a question and answer. We'll go through the questions of the people participating through Facebook and YouTube, and then we'll deal with the people. I see a number of people are in the green room already, and we may even have one or two more. So, and if there are any problems, if you can't hear Jeff, if he's talking too quickly, just put a comment in, and we'll try to address it, and we might even interrupt the proceeding momentarily. So, without further ado, I'm going to introduce Jeff. There's Jeff. You're very, very welcome. Great to have you, sir, today. And I'm going to bring myself down, which means that the floor will be entirely yours. And all you need to do, by the way, is tell me when you want the slides projected up, because I have to enable them to be added to the system. But once that's done, you have complete control. And I might try to minimize your photograph to maximize the slides, but you'll be audible and so on.
All right,
so
great.
Without further ado, the floor, Jeff, is entirely yours.
Thank you, Ian, and thank you all you members. You could go ahead and bring up the slides now, Ian, if you want. So this presentation is called General Relativity Inside Out, Dark Energy and Dark Matter. So my question is, can you guys see my cursor or no? I don't know if you can or not. But
I think no.
Okay, think no. All right. So I'll just describe what's on the slide and everything. So what we're talking about is, we have these concepts of dark energy and dark matter, and I have a framework called SIPNI, which stands for the Calculus, Philosophy, and Notation of Axiomatic Homogeneous Infinitesimals. It's a mouthful, but I want to talk to something about what are called homogeneous infinitesimals and proportionality. This thing is going to start out with seeming very basic, and I hope it's something a junior high student could understand. And we're going to go over some just geometry, and hopefully it's very simple. There's equations, but most of the stuff is just, is something bigger or something smaller. So hopefully it shouldn't be too bad. I've been working on trying to explain this as well as I can. A little background on me. I was previously a PhD candidate on a fellowship. I only had a dissertation left. In 2011, I was studying tensors for elasticity stuff. And I started reading about tensors that were in general relativity and about this thing called the cosmological constant. And it really bothered me because it indicated there was something seriously wrong with the physics I'd been taught. And I didn't know exactly what it was. I'd read that it was a constant of integration sometimes, but I understood calculus. I'd taken advanced calculus. I didn't understand exactly what this was. And as I read more, it didn't appear anybody else did either. So I started digging. I had a breakthrough last year in my research, and I am currently rewriting papers, and I'm slowly analyzing tactics for publication. Theoretical physics versus a mathematics geometry path during the spare time I have. And so, I have to think these things through in my head and try to figure out best I can. Fortunately, we live in a consensus right now in mainstream physics, this time we're living in right now, where the mainstream physics is starting to sound like natural philosophers. We're starting to merge, that there's something seriously wrong with our view of the universe. And I want to read this quote because it's important, because these are not natural philosophers. These are observational cosmologists who wrote this. And it's called the Dark Energy Task Force Report. And they said the acceleration of the universe is, along with dark matter, the observed phenomenon that most directly demonstrates that our theories of fundamental particles and gravity are either incorrect or incomplete. Most experts believe that nothing short of a full revolution in our understanding of fundamental physics will be required to achieve a full understanding of the cosmic acceleration. And you can do a search for the Dark Energy Task Force report and stuff. What this presentation is about is its initial attack on the mainstream view, not on the right side of this equation down below, but on the left side, on the geometry side. So that's what this is about. The goal of this presentation is I want you to understand implicitly how the cosmological constant can be a constant of integration in a theory of curved and straight lines, because this is what bothered me initially. I didn't know how this was even possible. The theory, the dark energy and matter, is going to be at the end. But my actual main goal of this presentation is to stir the pot towards natural philosophy. I want you to understand is that before I got into my PhD stuff, I would have considered natural philosophy. I would have read what it was. It'd be to say, well, this is a bunch of crackpots who don't really understand physics and everything. And my view of that is turned 180 degrees. And I would consider myself the biggest natural philosopher there is. I want you to understand how important infinitesimals are and lines are to how we write equations that describe the universe we find ourselves in. At least the one I'm in, and I would think the ones that you're in too. And you need to understand their limitations. I want you to understand that something called infinitesimals and lines are a language. I also want you to understand the importance of what was called the heterogeneous versus the homogeneous infinitesimal debate back in the 17th century. This should be within Natural Philosophy 101, is grasping the precise distinction between these two. I want you to understand the concept of how formalism and success of Leibnizian and Newtonian calculus ended interest in this debate about homogeneous and heterogeneous. That went away. Hey, we got limits. I'm going to try to explain this very simply, but it's helpful if you've had some calculus. I want you to understand how concepts of Euclidean and non-Euclidean geometry shape the relativistic viewpoint of our universe, of how the mainstream says these things. What I want to do is I want to foment skepticism of the current use of what's called the calculus, Euclidean, non-Euclidean geometry describing our universe. And I hope that you'll understand the basic concept of what I'm talking about by the time that this presentation is done. So there's a bunch of small stuff on here. This is just, I'm going to use Wikipedia. I actually, financially support it under fundraiser stuff. I think it's a great thing for lead in on stuff. And maybe not digging in. There's a lot of stuff missing, but for lead in stuff, it's great. If you were to open up the Wikipedia page for infinitesimals, you will find out that infinitesimals is a, what they really are is it helped develop, what was the calculus and everything. There's a thing called hyperreal numbers and what were derivatives. But you'll also find out there was a guy named Abraham Robinson who developed stuff called like non-standard analysis. But and that was recently in the mid 1900s. And what you're also going to find out is that a guy named Vladimir Arnold says they were good for, it's good that students know about these things, but they don't have a good command of them, but that's okay. But if you look at our laws of physics, you'll see like over on the right hand side of this equation, there's all these little they're called partial derivatives. And you'll see this little delta P and delta T. And these things originally came from the infinitesimal concept. So they're very ingrained in our laws of physics. This is what we use to describe the universe we're in. There are things called differential equations, and you will see the little du's and the dx's and stuff, everything. It's like, well, this is what we're using to describe our universe. And even when we get to integration, this is just the concept of summing the area under the line. If you look down at the bottom little thing there where it says calculus, you'll see a little dt there about summing things under the line. But there's the infinitesimal little symbol again that originated from infinitesimals. And then we have this concept of Euclidean geometry, where we starts off and they talk about planes and lines and things like that. This is still taught today, and we are all kind of taught what Euclidean geometry is. And then we get into this really complicated stuff called non-Euclidean geometry, and you see like surfaces here, and you got these surfaces are shaped like potato chips, and they're bending up and down. And we've got elliptic, hyperbolic, parabolic, and planar. And we have all of these complicated ways that they talk about geometry and these little K's here. So just imagine this is what we use to help describe, at least what I've been told, describe the universe. And then if we dig a little more into general relativity, if I look at the top left, it's tiny, but that's the Einstein field equation there. Where's my, but if I break out this little g here, that u and a v is actually a mu and a nu. I got something called the metric, and then I got my dx mu and dx nu. It's coupled up there with it. And I got this little drawing that comes from this massive book that's called The Bible of General Relativity. It's called Gravitation by Misner, Thorne, and Wheeler. And they said there's 3 different representations of a differentiable manifold or something. There's about an s squared. There's like some kind of rays emanating from it. So they said there's like 3 different ways to look at this thing called a manifold, whatever the heck that is. So we understand it's extremely complicated. And you dig even further in, you get basis vectors. You have all these things, flat space-time, one forms. I'm not asking you to understand these. I'm just looking at how complicated all of this thing is. Coordinate systems, world lines. And then you get into this cosmological constant problem with this lambda symbol here. It's an extra term in the Einstein field equation. And what you have two, you have to be careful about whose opinions you listen to. By that, I mean, to get a wealth of them. And you will find people with different perspectives on the same problem. Some people will tell you there's nothing wrong with general relativity. And that is a beautiful theory. But then you will have other people saying, like what that dark energy task force said, there's something wrong with it. And nobody knows what to do with this lambda out here on this extra term. And this thing is called sometimes a constant of integration and a scalar multiple of the metric, whatever that means. But it really bothered me about the integration constant. So you have all of this complicatedness. And what I want you to do is let's just stop for a second. And we're going to go back real basic. We're going to go back almost 400 years. And there was this, you've seen the dx symbol. It was invented by a named guy, Gottfried Leibniz, this symbol here. But the concepts of infinitesimal can trace back to over 2,500 years. But it was more originally to an Italian on the Italian peninsula, a guy named Bonaventura Cavalieri. And one of the great debates during that time was whether lines were made of non-dimensional points, called heterogeneous, or they're made of infinitesimal segments of line, which is called the homogeneous view. I would like for you to really understand what this means. And I'm going to go over it. And then we'll talk about what all that means. So there was a scientist that was known to Galileo named Evangelista Torricelli. And he was a brilliant scientist and inventor in his own right. He's well known to Galileo, like I said. And he could take a weird concept and explain it many different ways. So he was a great teacher. Cavalieri wrote massive books that nobody actually read. They would refer back to him, but they weren't actually reading them. But it was Torricelli who came up with all these examples to explain these paradoxes, to try to relay these concepts. Yes, 2,500 years ago, there's a book called Infinitesimals, A Dangerous Concept by Amir Alexander. And you can look up the concept of the infinitesimal. There's a timeline in there. Well, they will go back almost 2,500 years. And I'll talk about a paper. I'll give you some links to it so you guys could do some of your own research. So what is a heterogeneous infinitesimal? Well, I want you to understand is I got two lines here. See these two black lines here? There's one on the top and one on the bottom. If I asked you which line has more points in it, I think most people would say, you know what? That top line is it's longer, so it has more points in it. And you could say, well, look at a circle. If I take a circle and I draw lines out from the radius, the outer line, the outer circumference is longer, and it has more points in it, right? And that seems reasonable to most people. But that was kind of repugnant to some people like Torricelli, who said, how could I take points that don't have any dimension and add them up and I get a line of one dimension? If I was going to do a plane, how would I take these infinitesimally small or lines that had no width and stack them up like pages of a book and create area? And the same thing for volume. How do I take planes that have no thickness and add them up to volume? So philosophically repugnant, but this is kind of how people think. So what kind of Torricelli was talking about is that, it's homogeneous, is that if we're going to add something up, what we need to know is how do I add something up with one dimension and I create something longer. So imagine at the top you had B and D and a C and D, and they're actually made of little infinitesimal segments of line. And if I sum those up, well, I know which one is longer is because it's the one with the more segments in it. All right. And it got a little squirrely after that because you'd say, well, if I'm going to make a plane, then my lines would have to have thickness. If I was going to make volume, well, they'd have to be like sheets of glass. So, but it seemed to kind of make sense for a one-dimensional. So Evangelista Torricelli, though, he did not believe in the heterogeneous viewpoint. What he said was that, all indivisibles seem equal to one another. And that is points are equal to points, lines are equal in thickness to lines, and surfaces are equal in depth to surfaces is an opinion that, in my judgment, is not only difficult to prove, but false. And he came up with an example to show what he meant by that. He said, I'm going to draw a rectangle, and I'm going to, I'm going to label the points A, B, C, and D. And then he's going to draw a line down the diagonal from B to D, and he's going to put point E on it. And he's going to draw lines perpendicular down to G and F. This is pretty basic. But then he was going to move E down to D point by point by point. And he was going to do the same for F down to D and G over to D. Everything was going to go point by point by point. And what he said was the problem with that was that we already know that line AD has fewer points than line CD because it's shorter, but we just, if we're going point by point, then it's almost like the points in AD equal the number of points in CD because we went point by point. And then that would also go for BD. If you pick up a book like this one here called 17th Century Indivisibles Revisited, what they're going to tell you is that the current most advanced explanation for this is something called cardinality and magnitude. They don't explain what that means. They say that's how we're going to do it. And if you look for a further explanation on this, you're not going to find it. So we're natural philosophers here. Let's just dig this out and be a little bit more understanding of what it is we're dealing with here. And if I follow Euclidean geometry, I can use the property of what's called congruence. And I can take this BD line, this diagonal one, I'm going to lay it up there on the right, and I'm going to take my CD out, and I'm going to lay it next to it, my AD also. And what you see here is that, what Torricelli was saying was that my magnitude of my segments in BD were bigger than the ones in CD and were bigger than the ones in AD. So what he was meaning was that these are segments in this line and not points. And that all of my lines must have the same number of segments in them. It's just that the segments aren't bigger. Now, so what I have in there is something that says each line is intrinsically flat. So just give you a little clue here. What I mean by that is you can see that the line BD, the segments in it are the same, and the same for line CD and the same for line AD, but the segments aren't the same. If I happen to have a line, let's just say that where the segments weren't equal within the line itself, if my segments had different magnitudes within the line, I would call that intrinsically curved. So, but I'm just saying they're each intrinsically flat because the segment magnitudes are the same. So in BD, all the segments in that are the same, and all the same in CD, and all the same in AD. But if for some reason the segment magnitudes weren't equal in that line, I would call that intrinsic curvature. All right. So just to make sure, all I'm talking about here is they're intrinsically flat, means that my segment magnitudes are the same. You can see that they're not the same between the lines, but they are same in the line itself. But we said just a little bit ago, I could have lines, and if it was longer, I would just have more segments in it, and the magnitudes were all the same in each of the lines on the left-hand side. But what we realize is over on the right-hand side, I could have lines where the magnitudes are different, but all the left and right, the BDs and the CDs and the ADs, they're the same length. It's just a matter of how many magnitudes I have in it and what are the magnitudes in relation to each other. So let's write an equation for the length of a line. And now you might say, well, okay, well, I'm just going to sum up these segments and everything. Why you might not think that's that big of a deal. Just remember there was a guy named Bernard Riemann, all right, famous mathematician. And if you happen to look in his paper talking about, the foundations of geometry, one of the first things he said is that I don't have an equation for a line. So we're just going to assume we can compare lines by one's longer than the other. And we'll just go with that. So Riemann did not detail himself enough to write out an equation of a line to talk about the magnitudes and the cardinality. So I'm going to call the number of the segments within the line the relative cardinality. And I'm going to draw this segment thing here. I'm going to say that's the magnitude of each of the segments. So I know the line length simply by multiplying the relative cardinality by the magnitude. And that will tell me how long my line is. Pretty simple, basic mathematics. But wait a second. That means that we can have lines that have varying cardinality and varying magnitudes. You can see my magnitudes aren't the same, and neither is my cardinality in these lines. But I can know my line length just based simply off of the cardinality and the magnitude. But there's a problem with this. There's a principle called the Archimedean axiom. It says, you know what? You cannot just add infinitesimals to a line, because no matter how many times you multiply by that infinitesimal, you don't get a bigger line. There's something also called L'Hopital's paradox and everything. And just said you can't do this. We don't allow this to happen. But wait a second. In the mid of the 20th century, there was a guy named Abraham Robinson. He said, you know what? I'm going to call something hyperreals. We're going to do exactly this. And if you look in the middle of that paragraph, you'll see two hyperreal numbers are infinitesimally close if their difference is an infinitesimal. Now, Robinson said they were hyperreal numbers, but we're going to pretend that they're lines, okay? So basically, if I have two lines that are equal, and you can see my little RC1 dx1 equals RC2 dx2. Now, I've changed my notation here from the segment. I'll explain later. It's because of Leibniz, but it's the same thing. It's just a segment magnitude, right? It's just those little line segments. That's all it is. And my cardinality, my number, right? He says that if I add a segment to one side and make it longer, then the difference between the two lines is simply an infinitesimal. That's all it is an infinitesimal. So I have an infinitesimal difference between two lines. But wait a second. There's something called the theory of proportions and about homogeneous infinitesimals. What that says is that I cannot actually know the length of a line. All I can do is compare it to another line. So it's called the theory of Uticus theory of proportion. So on the right-hand side there, I can compare the length of two lines, but I can also say I can compare their segment magnitudes, And I can compare their cardinalities. So I can compare line to line. I can compare segment magnitude to segment magnitude. And I can compare relative cardinality to relative cardinality. It's just a ratio. Pretty simple stuff. All right. And just to beat this into you, there's something called solving systems of linear equations. So if let's just say I have one line that is 10 times longer than another line, then I could say, well, my cardinality is 10 and my segment magnitude is 1, and that gives me a line of 10. Or my cardinality could be 1 and my segment magnitude could be 1, and I could have a 10-to-1 ratio. But I could do the same way, many different ways. I can change the cardinality and the segment magnitude to whatever I want. I am free to do that, but I have to compare them. I cannot just say a line is a line. I have to, just think of this. We'll just call this homogeneous infinitesimal relativity. I can only know the length or the magnitude of one in comparison to something else. But like I said, what if the infinitesimals aren't the same magnitude within one line? Now, like I said, we won't worry about this just yet. But when you see that when I talk about something being intrinsically flat, all I'm talking about is my infinitesimals are the same magnitude. Okay. If it's intrinsically curved, then I'm just going to say my segment of my magnitudes, or magnitude of my segments are not the same between each other. And if you look in the middle, you'll see that dx with a little hat there, and there's a double-ended arrow. That is simply an indication that two magnitudes I'm comparing, two segments I'm comparing, are equal. So it's a 0. If they're not equal, then it would be either greater than or less than. Okay. So, and my dx with a little double-ended arrow there is just a way of writing the segment magnitude. Notation provides economy of thought, but there's a danger in that. So now that we know we can compare ratios of line segments and the relative cardinality and the ratio of the segment magnitudes, and we can do that to compare line length. So I can have 3 lines here, and I know how long they are relative to each other. And I look at these 3 lines and I know that they are of equal length because of the cardinality, the number of segments that are in them, and the magnitude of each of my little segments. Pretty basic stuff, and I hope that's the way you view it too. But we said these things are homogeneous, okay? Now, we're not going to do like Torricelli did, where he said, well, I must have lines or something of different thickness. What I'm going to say is that I can have little elements of length, but I'm also going to have little elements of area, an infinitesimal element of area. I'm also going to, if I want to go more than that, I'm going to have little infinitesimal elements of volume, because I cannot sum lines with no thickness and make area. Just like I can't sum lengths and make a line. Or I have to sum length to make a line. I also have to sum area, little elements of area to make area. I also have to sum little elements of volume to make volume. That's why when we say they're homogeneous. And you can go back to Torricelli's example to find out why you cannot sum length to make area. You cannot sum area to make volume. So over on the left-hand side, I've got this little block here, the square, and it looks like 2 little double-ended 2 lines that are next to each other. Those actually represent a column of little infinitesimal elements of area. Now, just due to how bad I am at drawing and everything, I'm going to make these little plus signs, and these little plus signs represent my area, my little infinitesimal element of area. Now, you might want to think of these things as little squares and everything. And it's okay to do that right now, but don't take that too seriously. Otherwise, you're going to run into what Descartes, he was a philosopher, he called the protruding parts. He had a problem with the protruding parts. So we're just going to consider those to be little infinitesimal elements of area, just like we did the line. The little segments. Now I have little elements of area. And I'm stuck with my notation, so I'm going to call the left and right the dx, and I'm going to call the up and down on this the dy, just for now. And they're flat, meaning that my dx's are equal to my dy's. It's little infinitesimal elements of area, each one of those, and they're all the same. So I have a little column of area, and I'm going to call that an areal line. So I can have a lineal line made out of little segments, and I can have an areal line made out of segments of area, just stacking them up. So that's all we're going to think about. And the line segments that represent this area and everything, they're the same between them. So we're going to call that intrinsically flat. Now, in a line, a lineal line, we just have little segments. If I squish one of those little infinitesimal elements of length up, where I'm just going to say it has a null length, I'm going to call that a point. So in my little areal line, which you're seeing here, my little stacked column of pluses in here, I can have a point here too, but I'm going to squish one of my little plus signs in the direction of the line. So a point in my areal line is just like a little symbol across. It's just, it has an element of length, but it has nothing going in the direction of the line. It's just a flat little, when I say flat, no, I shouldn't say flat. It's a squished little element of an area in my areal line. And so what happens if I wanted to just make a Cartesian coordinate system out of this, this would make it very simple, because what would happen is that I could have a block here made of little elements of area. And when I make my Cartesian coordinates, I know my background is flat. I don't need to know what the width of my dx or my dy is, because I just said they're equal. So what happens is that my coordinate points are actually just my relative cardinality. So if I want to count out how far I'm going out in this coordinate system, and I'm using little infinitesimal elements of area in my background, if I want to know how much area is covered, like by the 0.23 from the origin, I'm just counting out the cardinality. That's all I have to do. So the coordinates are the cardinality, or, because I also have my magnitude segments are built into it. That's interesting. So if I want to do something like, say, call it a coordinate transform, all I'm really doing is summing up more cardinality of the magnitude of the elements in the background. It's pretty easy. So I can use a coordinate system to do a coordinate transform, but all I'm really doing is just summing cardinality and magnitude. Not that hard. Oh, what if we want to use calculus? Okay, this is on the left-hand side here. You'll see that figure D7. That comes out of a guy's book his name is Jerome Kiesler, and he liked the infinitesimal concept, so he showed how to derive calculus using it. But remember, our dy and our dx on this, we're just going to say they're flat. So underneath that line that I'm integrating, I'm just integrating the number of my little infinitesimal elements of area. Well, that's pretty handy. But wait a second, there's going to be a problem with the notation. If you look in the middle there, you'll see a delta x and a delta y. Well, we have our notation for a line. So the delta y is actually the relative cardinality of the y times the dy, and the delta x is the relative cardinality of the x times the dx. But the dy and the dx we know are the same, because we did a coordinate system with that. Oh, okay. So Leibniz's notation is a little unfortunate, because if you look at dy over dx, we've already said that dy and the dx in the background are the same. What we're really doing is we're comparing the relative cardinalities of the infinitesimal elements of area. It's RCY over RCX, and we're just setting RCX to 1. And we're comparing how many infinitesimal elements of area I go up. So if I'm comparing a line, the derivative of a line, I'm just comparing how much the cardinality of the homogeneous infinitesimals change relative to the background. But it's hidden in Leibniz's notation of dy dx, because we think of dy as going up and down. But if the cardinality, if I know my dy and dx are the same in the background, my cardinality of the y is not changing, then it's a 0, because there's no difference in cardinality from the background. That's just a straight line across the back. So I can use cardinality to tell me whether or not a line is parallel. I can also use cardinality to tell me whether or not my line is going up, a positive derivative, or I can use it to tell me if I'm going down. So that's interesting that, you got to be careful about Leibniz's notation on the dy and the dx, because really all we're doing is counting cardinality of homogeneous infinitesimals of area. So dy dx can be a little misleading. It can be bad notation. And this is why I ended up in my paper, you'll see, is I had to change the notation to make it consistent. I couldn't use just Leibniz's. dy and dx didn't make sense if they were flat in the background. So this is why Torricelli's example matters, because it pulls out the difference between cardinality and magnitude. If you look between my little plots here, in Leibniz's notation, dy and dx in the background are the same magnitude. It's flat. But what I'm actually doing is I'm holding dy and dx constant, and I'm just examining the ratio between the cardinality of y versus the cardinality of x. But Torricelli's example is the exact opposite. What he did was he held the cardinality of the lines that he was comparing. Remember, everything is relative when it comes to homogeneous infinitesimals. So he was holding the relative cardinality between the lines constant. If you look over on the right-hand side, you'll see the BD, the CD, and the AD. Those are nothing. I have 1, 2, 3, 4 in BD. I have 1, 2, 3, 4 in CD, and I have 1, 2, 3, 4 in AD. The cardinality of the lines are the same, but I'm changing the magnitude of the elements. Whereas in Leibniz's notation, it's the exact opposite. He's varying the cardinality, whereas Torricelli was varying the magnitudes. And that's why Torricelli's example was more difficult, because you didn't realize that he was actually holding a cardinality constant, and he was examining what would happen with a change in magnitude of the homogeneous infinitesimal. But so let's go back to this relative cardinality and this analysis of, is it about cardinality and magnitudes? Remember the circle on the left-hand side? We took, let me get a drink here. We took a circle and we said, you know what, that outer radius of that circle, it has more points in it because it's longer. The circumference is longer. It's got to have more points. But when we sweep that line around the arc, okay, every time I sweep an arc out, the number of arcs on the inner circle equal the number of arcs on the outer circle. And that is because I am dealing now with area and I'm not dealing with length. I'll give you another example. Over on the right-hand side, I have these two boundaries here. This actually represents areal homogeneous infinitesimals, my little blocks of area. That's just one linear areal line. It's a stack of little segments of area. But I go taper down as they go down. Tapering, I think, is the word that Kepler used when he was talking about it, when he derived his planetary orbits, because he was looking at the kind of the same thing. And he said, well, if my little segments go down as I go down, my little infinitesimal elements of area go down, and I place those next to each other, remember what I said about my points are just being little squished areals? The number of segments within each line as I go around the circle is the same. So now the cardinality of my circles is the same. The reason the area increases is because my infinitesimal magnitude is increasing. So on the left-hand side, you place lines around there, and the cardinality is different between the two lines, making one along the other. But on the right-hand side, the cardinality of each of the circles is the same, because I'm just examining the area with, crosswise is the width of my areal homogeneous infinitesimals. Let me make sure you understand what I'm saying here. I have areal lines, and they're made up of infinitesimal elements of area. So as I go up, if you look across the dy's, they're the same magnitudes left to right. That is the circumference of a circle. Okay, if I squish that one down, the same for the ones below it. The cardinality of the circles that I'm making out of these does not change. The reason the radius changes is because the magnitude of the infinitesimal is changing. That's a distinction here between cardinality and magnitude just on this. All right. Now let's tackle a voluminal line. These are just stacks of little elements of volume. All right. Now, just like I said before, where I could squish an areal element of area and make a point, I'm going to do the same for a voluminal line. So the three little crosses that you see there, it's like a plus sign with an extra direction on it. That is an element of area. But if I squished one of those down flat, I would end up with this little rectangle. And those are points in a voluminal line. So if I take an element of my line and I squish it flat in the directional line, I now have little elements of area. So let's look at the left-hand side here. And I don't have a little cursor, but you can see the little dxn minus dxn1. What I'm doing is I'm just examining how my dx's change, or the difference between them across my little sheets of little squares, those parallelograms. Okay, I'm just examining across that. Does my dx, as I go across it, does it have a different magnitude from one to the other? Well, if it doesn't, then I simply say, well, it's intrinsically flat across that little segment there, which is nothing more than a squished voluminal element. That's all it is. And the same for the y, all right? So if I take the y direction, you can see my dy in there, and that is the kind of the line that's pointing out the page. Now, I've changed my axes here, but it doesn't really matter. You can figure if you look at the y on the top of the rectangle and the y below it, if they're the same, then it's intrinsically flat y's. And I'm just going to keep this simple, and I'm going to say that if I had a dz going up and down, so you can see I've turned my dz sideways. If those have the same magnitude going across this little element of area here, then I'm saying it's intrinsically flat going up and down. So this is an intrinsically flat voluminal line. It's not that bad. Now let's look at the right-hand side. If my dx's here were actually getting smaller across this little element of area here because I've squished one of them flat, then I would say it's intrinsically curved as we're going down. All right. So that's not too hard to understand. It's not advanced mathematics. Now the y in this image, I'm showing that the y is getting smaller in magnitude going across this little element of area also. But I've decided to, going across this element of area, I've decided to keep my z's the same. So the z's are not intrinsically curved, but the x and the y's are intrinsically curved across this element of area as we go across this. So let's look at something interesting here. Is that, remember how on the left-hand side with the circle I had my aerial line coming up? What if if I did that with a sphere, and I took these little intrinsically curved voluminal lines, I made a sphere out of it. What's really interesting is that it has a lot in common somehow with what Misner, Thorne, and Willer were calling a differentiable manifold. And that's pretty interesting because they say each ray intersects precisely once. And we know if I made a sphere out of these voluminal lines, that the cardinality of every sphere would be the same. Even the reason that the area on the surface would change is because the magnitudes would increase as they go up. Just like the circle, the circle radius increases because the magnitude of the infinitesimal increases. All right, it'd be the same thing for a sphere. And it seems to, it has a lot of similarity with this manifold concept. All right, well, let's dig a little deeper. And technically what this is called is Gaussian curvature. And I have these things called the principal curvature parameters, these K1 and K2. You don't have to really know what they mean right now, but I'm just going to explain it my way. If you look at the bottom here, you'll see a little table. It says principal curvature K1 and K2. And then that is Gaussian curvature way of looking at it. And I have my intrinsic curvature of dx and dy as I go on my little voluminal line. Now it says for elliptic, if you look up that picture for elliptic, it shows that both of them are curved downward. So all it cares is that the curvature parameters have the same sign. Well, if I go over up to the top left and I look at my voluminal line, if my dx across that little flat rectangle was going smaller and my dy was getting smaller, they would have the same signs too. So what's interesting here is that that kind of matches what they're talking about, a curvature of this elliptic surface here, which is a point that somehow has area. So that's interesting, is that my point on these things have area, but so do my voluminal lines. Now, hyperbolic, they said, well, they just have to be opposite signs as K1 and K2. So if I take at the top left my voluminal line again, if my x's as they go across, let's just say my x gets smaller, but my y gets bigger as I go across there, well, that would kind of give me the same shape as the hyperbolic. It looks like a potato chip or a saddle. That's interesting. That's a heck of a coincidence. Now look at parabolic, and they say, well, one is 0 and the other is positive or negative for the curvature parameters. But I go back up to my voluminal line and I say, well, I'm going to make my x flat across that little rectangle area there, which means that my x isn't going to change. It's going to have the same magnitude. But my y is going to get smaller. And I look over at their little parabolic image. Well, that kind of matches where it would be flat across that little piece of area, and it would be bowing down on the other. That's a heck of a coincidence. And then on the planar, the curvature parameters K1 and K2 are both 0. Now, if I go back up to my voluminal line, I'm going to switch back a couple of slides here. Remember this voluminal line here on the left where the x's and the y's were equal across this thing? Well, it's just kind of ironic that that would seem to match the curvature parameters were both 0 and they call planar. So I can tell what kind of surface I have just with voluminal lines. So this is why I'm suspicious of relativity and the derivation of all the current laws of physics. It appears that general relativity is treating homogeneous. Wait, let me just back up here. What I'm telling you is I'm lying to you, all right? None of this is real. There are no voluminal lines. There are no circles. There are no squares. There is no calculus. There are no coordinates. There are no coordinate transforms. All I actually have are homogeneous infinitesimals and cardinality and magnitude. Remember when Jerome Kiesler said it was just a number? None of this is physically real. This is just an abstract concept that we use as a language, okay? I'm going to get into that a little bit more. It appears that general relativity is treating homogeneous infinitesimals as basis vectors and is setting their magnitudes to a 1 for flat space. I'm going to explain this a little more. The cosmological constant is said to be a constant of integration. The cosmological constant is said to represent the energy density and pressure of the vacuum, which could be some kind of fluid. When I say some kind of fluid, you can read the report of the Dark Energy Task Force, where they are trying to treat outer space as some kind of fluid. The analogy comes because they are saying that energy density and momentum that are in general relativity, it is directly derived from the analogy of the energy and momentum of particles of a perfect fluid. So they said a planet was actually, they're going to treat it as a perfect fluid. And they said that the particle densities of this fluid is the energy density, and the momentum of these particles is the pressure. So they had this analogy that matter was made up of this perfect fluid. The theoretical value of the cosmological constant is many, many orders of magnitude higher than what quantum theory predicts. It appears that a manifold can be derived from homogeneous infinitesimals. I'm not aware that any of the originators of non-Euclidean geometry ever attempted to use intrinsically curved homogeneous infinitesimals when they were developing non-Euclidean geometry. What all of these guys did, like Gauss, Riemann, these other people, they just tried to take intrinsically flat lines and say whether or not they were parallel or not, and didn't even have a good definition for parallelism. I'm not aware that anyone has defined Euclid's parallel postulate as a conservation of relative cardinality times segment magnitude. So what parallelism appears to be is just a form of geometry conservation derivable from the postulate of homogeneous infinitesimal proportionality. The Ricci tensor is said to represent changes in volume. I'm not yet aware that manifolds have the z-axis concept within their derivation. I'm very suspicious of special relativity because none of the ether theorists who were trying to go against it, like Hendrik Lorentz, ever used intrinsically curved magnitudes of infinitesimals. And the proper time, the proper lengths and everything suspiciously have a lot of the same properties as intrinsically curved magnitudes. So what I'm saying here is that my hypothesis is that the metric is not a metric, it's the relative cardinality. When you look at this G mu nu, D mu nu, these are not space-time coordinates. This is relative cardinality times some kind of magnitude. I can philosophically assign anything to these magnitudes and do what I want with them. I can make these hot dogs, I can make these hamburgers, and I can count them out, and I can make my hot dogs bigger or not. If I can have a coordinate transform of space-time coordinates, I can have a coordinate, not a coordinate transform. I can do a density and pressure transform, just like you can do one for coordinates. Realize cardinality and magnitude are not coordinates. This is just an abstract concept, okay? So if I wanted to, I could make the flat space-time an unstressed elastic medium. And then I would do, instead of doing coordinate transforms, I would do density and pressure transforms of the medium. And there would be no way to know for sure which one it is if they were exact same. But remember, this is a language. If we have an ether and that ether is not flat everywhere in the universe, it's going to show up because of the changes of pressure and density. All right. So I think the general relativity is backwards or inside out in two ways. By this, I mean that the boundary conditions need to be changed using the cosmological constant. Instead of utilizing a 1, like for basis vectors in Newtonian approximation, it's going to be logically more like lambda minus lambda 2 phi is equal to this, approximately equal to this 1 minus 2 phi. So we have the Newtonian approximation. The magnitude is almost correct, but the boundaries are not. That means lambda is the density of the vacuum, but energy density is the change in the density of the vacuum. So our symbology is not quite right. So I want to make sure that you understand the difference between relative strain and absolute strain. So strain is just a stretching of a rod, okay, or a compression of one. And we have this sigma or epsilon signal up here. So absolute strain is when you add cardinality. I can tell the difference between two lengths by adding cardinality. Or what I can do is change the length of them by changing the magnitude of the segments on the bottom there with my little smiley face. All right. Let me explain the two images on the left. So what general relativity does is it says I have a planet, something like that, and it actually stresses space-time. And it's using a heterogeneous argument using points. And it says that as the points get closer to the density of this pressure fluid, the distance between the points gets smaller. And if it gets small enough, these points will actually overlap, and you will get the Schwarzschild radius. But it says in outer space, there was not supposed to be anything. And we just said that it was flat, meaning the points were all equidistant, or maybe I had a basis vector of a 1. Sorry, somebody's doing dishes. But what they're trying to do now, if you look at the dark energy task force, what they're trying to do is put this lambda out there, or this rho p over thing, critical density and everything. And you can get this from the dark energy task force report. So beforehand, we were told that their energy density and momentum were modeled after a perfect fluid, and they curve space-time. So they're just basically stretching the distances between points. But if the distance gets small enough, they overlap, and we get a Schwarzschild radius. And they said, well, when the points get equidistant far out to the left, then what's going to happen is that it's just flat, okay? It's just equidistant points. But now they're trying to put a perfect fluid out there. So what this is saying, what I'm saying is that if you look down the right-hand side, down at the bottom, this A is between the distances here, the magnitudes. This is just a geometric magnitude. So for dark energy, what would be happening is that the magnitudes of the infinitesimals are stretching out. This is not a 1. So this is just nothing more than stretching of magnitudes, just changing the, not the cardinality, but just the magnitude in this example. And this is, if I model this as a perfect fluid or an elastic medium, what I'm saying is, the density or the strain in my medium is changing everywhere. Now, you got to be careful how we interpret this. I'll go over that. And what I'm saying is that if we model all of these magnitudes as a perfect fluid, whenever there is a wave in it, then the magnitudes of the of my segments, or actually my voluminal homogeneous infinitesimals, change, and I actually get a wave pattern through this fluid. And if I want to do a Now, instead of doing a coordinate transform, I would do a density and pressure transform using the exact same style that is required of homogeneous infinitesimals when we go back to the proportionality. So remember, if it's flat, it's just an unstrained elastic medium. If there's a curve in the fluid and everything, then I have to use not coordinate transforms. I have to use density and pressure transforms. We're still, bound by the same limitations of homogeneous infinitesimals that general relativity is. We just don't use coordinate transforms. We would use density and pressure transforms. So the takeaways from this is that RC times the cardinality times the magnitude and their sums, it follows Uticus theory of proportion. And these three little plots here, these are all the same thing. They're just different ways of looking at cardinality, magnitude, and their sums. All four of these plots, whether I'm looking at a square on the left and I'm examining how these things move down, whether I'm comparing line segment magnitudes and their changes in them, if I'm comparing calculus where I'm just examining the cardinality changes of magnitudes of a background, or Cartesian coordinate system, or any type of coordinate system. All I'm doing is looking at cardinality and magnitude. That's all this is. So the other takeaway is the difference between Euclidean and non-Euclidean geometry. Euclidean geometry would just be flat segments or flat areal lines or flat voluminal lines. If they're all just the same magnitude, that's flat. Non-Euclidean geometry would be where the magnitudes change. So they're intrinsically curved. My argument is there's a difference between homogeneous infinitesimal relativity versus general and special relativity. I think that general and special relativity are a misunderstanding of the Uticus theory of proportions and the real number line, basically. My latest paper, I did put a copy up on Vixtra. I don't have access to archive, so I put it up there if anybody wants to bother to read through it. It is I had an earlier paper, which I did submit to a journal. I tried to get it proofread. I paid I'll pay $900 for somebody just to proofread it and make sure it was organized correctly. And they kicked my money back and said they couldn't find anybody that could even proofread it. But my paper is into a journal. They had an automatic preprint process, but they kicked it back because they said my paper was theoretical. And they haven't signed an editor yet for my paper, but it will probably get rejected as soon as it gets an editor. And I'll have to figure out a different tact. So even if you don't like my research and you think I'm full of crap, please support the John Chappell Natural Philosophy Society. It is my view now that the human species may one day realize it owes a debt of gratitude to volunteers that have kept it going. Please let me know if I've achieved any increase in skepticism, whether you're a junior high student or a high school student or growing up and everything. If you also want to help proofread my paper or clean up my axioms or criticize my idea or methodology, or maybe an offer of assistance, you can find my email there. My name is Jeff Baugher. Worst case scenario on my research here on this little presentation. So if I somehow died 5 minutes after this presentation and you happen to be viewing this video 100 years from now, and you're trying to look at alternatives to relativity, just some things I would like to pass on before the end of the video is that my dialectic view is that there's the reality that we exist in, and there's my view that cardinality, maybe ordinality, and magnitude may be the best language we have for describing it. So we have our physical existence, but we also have our language for describing it. It's not calculus. It's not Euclidean or non-Euclidean geometry or coordinate system or anything. It is simply just these concepts of cardinality, ordinality, and magnitude. We like to think of them as lines, but that can be misleading because a line can represent many things. It can represent the magnitude of temperature. It can represent how happy I am on a certain day. It can represent the length of a line that I've gone, but it can also represent the difference in clock rates. It can represent the difference in length of stuff. So you have to be careful. Lines are a language, and we get confused because what we like to think of them as length, physical length. And while that can be helpful, it can also be misleading. I was told that everything that could be tried had been in general relativity, but I have not found that to be true on the geometric side of the Einstein field equation. So I do not assume that is true on the right side either. And also keep in mind the symmetry present in nature. Best case scenario, if somebody did like what I was doing here, is just want to say is that one of the biggest requirements we have for keeping our species alive on this planet is to find different energy sources other than fossil fuels, such as nuclear fusion. The best strategy we could have for that is to have proper laws of physics. Now, I'm just one person, 54 years old, and I cannot accomplish this by myself. That just wouldn't make sense. So if you want to help out, you can make this video go viral, or maybe help out the John Chapel Natural Philosophy Society, so that me or somebody else, we may get help, assistance with the ideas of rewriting the laws of physics and deriving the constants of nature. And I also have some ideas about quantum mechanics. I greatly appreciate your valuable time, all of you natural philosophers. And that is the end of my presentation.
Well, thank you very much, Jeff, for that intriguing lecture.
Was it understandable at all?
Well, we'll soon find out. I mean, to me, somewhat. I was very interested and taken that you were going back to fundamentals, and in particular, you stressed the advantages of the natural philosophy method, which sometimes is put down a bit in physics circles, and we can be going to the other extreme, just looking at some fairly basic experiments and just comparing them with what applies. So you're going back very much back to fundamentals.
Yes.
We can see how maybe the Leibniz system has come in. We're using it every day, these sort of infinitesimals, whereas maybe the Newtonian notation, quite different, maybe just putting a dot on the variable or something like that, is not as obvious. And yet, when we're dealing with very complex differential equations, we tend to use the Newtonian system because the Leibniz thing can be very extensive and long-winded. So I don't know. We're going to see people's views now, but I mean, I think you're beginning something. If you want my candid view, I think it's very important to look at these fundamentals, but I think one has to go a bit further to apply them to very, very significant theories which are accepted, like general relativity and
right.
This lambda business, which has been described as a fudge factor. So, and mind you, I'm confident that you're doing that because of our discussions recently and the fact that you have a paper in publication. I was intrigued by the business that despite paying $900 or something, that they couldn't get somebody to review it. So, so it can be a bit off-putting to people who are not so concerned about fundamentals. But I'm positive about it, although I think maybe there's more to go. Okay. Let's, with your agreement, see are there any major comments that you can deal with, and then we'll actually in the private chat. Not all are to be read, just examples of web page. Yeah. I see, Jim Keane has been making a lot of comments, and I'm sure he will, because he's extremely interested in this whole business of discreteness versus continuity. And this is basically, I suppose, what I mean, is the calculus discrete or continuous? You have right. Discrete quantities, which in the limit become continuous, I suppose.
Right. So you have this limit concept and everything. And I just want to make sure that we understand that the language here is discrete, the segment magnitudes, but I'm not saying that the reality we live in is. I'm saying the language we have, this is the limitations of it, segment magnitudes. I'm not saying that is our reality that we live in. I just simply, that's the nature of the language. We're trying to describe because I do not believe that nature is what we live in. From what I understand of quantum mechanics and the way I view it, is that it actually is discrete. If you want my philosophical viewpoint, I think we're all just sentient waves in a medium, and it's particular types of waveforms. That is what I think we all are.
Okay, well, that's a very interesting comment, and I think we may be able to delve into that a little more. But just to start, maybe a little controversially, Robert Kay says, I suppose in his view, a line is made of points. I'm not sure that I would say that a line is made of segments.
Right. So he's making the same argument back as Cavalieri did. back in the 17th century, is he's saying it doesn't make sense that it's points, but that's where you have to be careful about your bias about when we use our common sense to derive what we think of. We think the earth is flat and everything, and we think the stars were pinpoints of light. So you have to go. So geometry of how we view things can make it confusing. So it's very tempting to make lines heterogeneous. But I believe that's also been the problem with natural philosophy, is not getting past that. I believe that's been one of our limitations in our field.
Yeah, I mean, just following on from that, he says then your segments are infinitesimals.
Yes, that is correct. My segments are infinitesimals. That's exactly what they are. That's all they are, is infinitesimals. I'm using the drawings as a to basically give information about how the infinitesimals don't always have the same magnitude. But there's also something called George Cantor's transfinite numbers. Transfinite numbers are the concept that infinity can have different magnitudes.
Yes.
So I'm also saying that infinitesimals can have different magnitude and infinity can have different magnitude. That's fundamentally what I'm saying. But I didn't originate the idea of transfinite numbers.
Because we were first taught that, for example, there are as many odd numbers as there are numbers. But then we looked into Cantor's ideas and
Yes.
what you just said, that perhaps they're a different nature. By the way, just clarification, John Hodge is just asking, in your exposition, is flat equivalent to Euclidean?
Yes, that is exactly what I'm saying. Euclid's definition of a straight line was a line that lies evenly with the points upon itself. So if you think of flatness being the segments are equally the same, don't know how big they are, but the magnitudes relative to each other are the same, that matches the definition that Euclid had for being a straight line. So you could, the way Bernard Riemann said was that lines could compress and stretch, but he didn't have a way of describing how that stretching and compressing happened. But if the infinitesimals that are within it are all the same magnitude, that's flat. But if the infinitesimals compressed and got bigger, that would match what Riemann said about curvature, about his idea that the lines could somehow be stretched. Magnitudes changing, the segments of the infinitesimals, matches what Riemann said about infinitesimals, about his lines that changed magnitudes. How you could take a plane and stretch it over a sphere is because, in his view, you could take this plane and stretch over a sphere and you would stretch the lines. What I'm saying is I could take a flat line, the segments are the same, and when I bring it down, I'm actually changing the magnitude of my infinitesimals. That these are actually the same thing, but infinitesimals changing magnitude is a better description, is more quantitative, I would say, and I think it's philosophically better. And it all simply comes from the concept of magnitude, cardinality.
And I wonder what you think of Jim's idea relative to what, in a way, because he's saying he always smiles at curved geometries. They have to be curved relative to the flat 3D.
That is exactly right. You don't know. If I take lines and I say that these are flat and I say this is a straight line, I don't really know if one is, I can't just say one of them is the same to itself. You always have to have something in reference to something else. To have a flat 3D Euclidean geometry, the squares and everything, I can tell that by looking at the other axes and everything. So I can say one is relative to the other, but the whole I wouldn't know. I have to have something else to compare it to. You always have to have something else to reference it to. It's basically comes back to Eutych's theory of proportions. I don't know the curvature of one thing unless I have it to compare to something else. Whether that is a flat segment, I don't know. If I have one segment, I don't know if that segment is curved or not unless I have another segment to match it to. If I have a bunch of segments and they're all the same, I can compare a bunch of other segments to them to find out the curvature. I'm comparing them.
It's maybe analogous to the sort of this stretched plate they have to show the curvature of space, giving rise to gravitational effects, maybe balls coming down. But I mean, why should it move unless there's some force already bringing the ball down, into this puckered area?
Right. So let me explain how a voluminal line would work. So I think that my view of it is that matter and energy moves not as a linear line, but as a voluminal line. And it's like, well, how can I have a line be curved and straight at the same time? So you imagine you're going forward with a voluminal line, okay? And all I'm doing is I'm comparing the axes to it. If those are intrinsically curved as they go down to the right, All right, that's intrinsically curved that way. But as I move forward, I'm comparing my magnitudes and my segments of my X and Y going forward. Even though they may not have the same magnitude, if the next ones do, that's a straight line to whatever it is, that wave that's moving. The straightness doesn't have to do with the magnitudes, the relation to each other. It just has to do with the magnitude of the next one it's going to. If it's the same magnitude, that's straight, even though everything I'm in is curved intrinsically as I go along. And I think that's ultimately that's what's going to happen with special relativity, is that if you're co-moving with a wave, and your line is simply whatever it is. If I watched it go by, I would see a bunch of lines curving and uncurving as it went by, back to flatness. But if I'm co-moving with it, then the line that I have traveling with me, I'm just watching the next line. It looks straight. Watch the next line. It looks straight. So that's why it looks straight to me. But if there's an acceleration or a deceleration, then I have a change in the magnitude of the lines, which represents a change in momentum and energy.
Okay. Well, what do you answer this basically? Michael says, are you conceiving a sphere as an extension of a point in 3 dimensions?
I'm saying that a sphere is actually like what we think of as a 3D sphere is actually composed of 3-directional, I don't want to call it dimensional, 3-directional voluminal homogeneous infinitesimals. So all this stuff about projective geometry and everything, I think is a misunderstanding of the basics of homogeneous infinitesimals. If I'm going to make a sphere, if I'm going to make anything out of volume, it comes from a element of volume. So I can either look at the cardinality of how many of those are in there, and that's what I'm doing when I sum up a sphere, the area or the volume of one. There is the projective geometry where you say you project the geometry onto a 2D, I think is that, hey, I'm going to take all my cardinality of my volume, squish it down to the cardinality of a circle, and it looks right. But I think that's where the concept is missing, is to understand that there is homogeneous infinitesimals. And then with this projection of down to a 2D is that I'm just taking a 2D slice of my voluminal homogeneous infinitesimals. I had a volume homogeneous infinitesimals, project it down, and now I'm just looking at a grid for a circle, and those are flat pieces of area now. I think that's the misconception. I don't know if that helps or not.
I'm not quite sure what sort of quick explanation Robert K wants to this. I mean, he's in with the sine and the cos and so on, whereas in hyperbolic, the hyperbolic terms, the sinh and the cos and so on. What do you mean by explain? That's the way things are.
I'm a slow person, so I would have to draw it out, or if he wanted to submit it to me in a paper or something, or write it down or something, and I could take a look at it, and then I could easily submit my the area stuff like in there. I would use my definition of a line for area and everything, and I would show him how hyperbolic geometry, what he's talking about here, I would do my best to show him how I could resolve this with axiomatic homogeneous infinitesimals. And to be fair, if I'm correct about what I'm doing, and I'm not just some moron that doesn't understand geometry and everything, these things do need to be examined. And either what I'm doing is better, or there is something wrong with how I'm thinking. And, I want to check my own bias too. So I have no problem with somebody sending me problems and saying, is this correct? I might be slow when I go back about it and everything, but I don't want to fool myself. I don't think any natural philosopher wants to fool himself, but I think that's why we're natural philosophers, is that we believe other people are fooling themselves. We believe that, after looking all of the evidence come in, we believe that mainstream physics is fooling themselves. I don't want to fool myself. If I'm wrong, I want to know why I'm wrong. And, if you have a good equation to send me and said, hey, does this match what you're doing and everything? Then send it to me. I'll take a look at it. Maybe I'll learn something new, and maybe I'll find a new way to be able to explain my research.
So thank you very much. I mean, perhaps we may take that as an invitation to submit any specific ideas to you for validation or explanation. That'd be very valuable if people found some of the material a bit overwhelming.
Okay. And I want to just make another comment, is that theoretical cosmologists have never had an ether to play with, so they don't really have so for like the halos of dark matter. And what you're actually seeing is just some kind of curvature out there where there's no matter, and there's not enough matter where there should be. If this is just a change in the density of the ether, they have not had time to be able to absorb the similarities between coordinate transforms and density and pressure transforms. So that concept's never had. So stuff like redshift of light and everything is always taken from the viewpoint of, well, it's got to be because things are moving away from us. Things could be very backwards to how we're viewing them. And I'm just going to spitball here is that, we have this expanding acceleration, but it also could be a decelerating contraction. If things are completely backwards to how we think they are, then with this redshift of light we're seeing is actually maybe the density of the ether is getting thicker, and we just have it backwards at the redshift. So instead of a big bang, you could just say, well, maybe the universe was real fizzy at one time. Everything was just popping in and out of existence, all these basic particles and stuff. And maybe somehow, statistically, the antimatter faded away. But when it did, all was left was us and the cosmic microwave background. And now because the antimatter disappeared, the universe is contracting. This is a spitball. Don't take it seriously. But it's the kind of ideas that you need to rethink all this stuff about cosmology. If you've ever seen these pictures of where they say the universe is closed or open, everything, all this appears to me as to be a misunderstanding of homogeneous infinitesimals and how the magnitudes can change.
There have been a few comments coming in, which I needn't put all of them up, about string theorists. For example, Michael Charrier, I hope I'm pronouncing his name correctly, says, that's one of the reasons maybe there's resistance to this is that string theorists would never let it through. And then Andrew Castro, is maybe he thinks string theories are relevant and so on. And I'm going further down the comments here. So have you any comment, good, bad, or indifferent about?
Well, I've read what everybody else has about string theory, and I'm not an expert, so I just go off of what other people say about string theory. Obviously, I know how string theory has not gone as far as it was predicted to. That the person that originated no longer believes in string theory. I know that the Large Hadron Collider, they discovered what they said was a Higgs boson, but they weren't looking for supersymmetry and they didn't find it. So but I also know that there are a lot of physicists out there now who are saying, crap, because string theory is the only game in town and they've got nothing else to go on. They are looking around saying, we need something new to try. So my thing would say, hey, why don't you try cardinality and homogeneous infinitesimal magnitude? If you study general relativity a lot, these words would mean a lot to you. Homogeneous, manifolds, all these other things, you would understand the background. So, but this may never get into somebody who studies theory at that depth. So I think from my perspective, string theory is a dead end. If I was a young student and I was coming up and I had to look for theories to go into to make a living, to try and make some kind of impact in science, I would not choose string theory just simply because of nobody else has made any advancements in it. I would look for something new. Maybe I'm wrong. Maybe my stuff is crap, but maybe homogeneous infinitesimal relativity is something new to try. So,
well, the sort of identification of the cosmological constant with dark energy and my use of the fudge factor, I think Kev, who's living close by to me, relatively close by, has taken exception to that. I think Jim used it as well, but he thinks it's really excellent. It's a response to observation, good science.
Well, and just to make sure I'm clear, when I was told the cosmological constant was a constant of integration, I didn't understand it. Is that in calculus, a constant of integration, if you look just at the cardinality and the magnitudes, is simply a column of area that is constant along. Okay, I can't derive a flat line. I can't take the derivative of a flat line. No matter where that line is, as I go up and down with my little things of area, as long as the number of them are constant, that's a flat line, and that is a constant of integration if you go backwards. Okay, any constant number, right? The same thing when they say with the constant of integration in general relativity is that the metric, if it is the same as I measure along, it's no different than what is being shown in calculus. I'm just simply trying to find the derivative, the change in cardinality of this thing. And that is the analogy that you get. That's how I know that the cosmological constant is a constant of integration, is because of, if I go back and look at cardinality and magnitudes, it matches what calculus shows. Calculus is just a straight line, and I can't take a derivative because nothing changes, so my cardinality doesn't change. It's the same thing in the Einstein field equation. If it's just a constant number, then nothing changes. No number of them change. And they're analogous the same. They're actually very, very, almost exactly the same, except in calculus, you use areal homogeneous infinitesimals. And in general relativity, or at least my view of it, you would use voluminal ones. But it's the same concept.
Well, it's interesting to get your take on that, because there's some further discussion on it, which perhaps we don't have time to go into in detail. Quoting Feynman, complete skepticism about it, and others saying that the string theory, is working, and so on.
Well, we are at an interesting time. I think that if you look back in the history of physics and everything, whenever things started going really bad, is whenever people started trying to come up with new ideas. And we know right now is really bad. It's the worst time we've ever had in physics, because we have two theories that just absolutely do not match. So even if I'm wrong, natural philosophers, I think, is the way to go to, because mainstream physics is now saying they're wrong too. So let's look for new ideas. And I think that's maybe where we're going to find our new ideas, is stuff that's not going to be allowed in universities. Because I'm basically saying, there's no calculus. I'm saying there's no coordinate systems. All of these things are just made up ways to look at homogeneous infinitesimals. In a PhD program, I would get kicked out of university if I said that. But whereas in natural philosophy, I'm allowed to express these ideas.
You certainly are, yes. Well, we may, if we have time, come back to some of these questions, but perhaps it's time now to go into a more full discussion. And I know there have been some, private chat comments coming in, but I'll probably bring people in from the green room one way or the other. But if there's anybody who has pressing comments to make and he wishes to raise his hand, we'll put him in first. He'll be at the top of the queue. Harry Ricker is there. So good day to you, Harry. You're up now, and we'd like to hear what you have to say.
Okay. I got a couple of questions for Jeff. One is, Jeff, is your background as a mathematician? You didn't really make that very clear. I don't really understand where you're coming from. Are you coming from this as a physicist or a mathematician? Or...
So my undergrad was electrical engineering. And when I started studying my PhD
you're
program,
an electrical engineer like me. Okay, got that. So did you continue on?
When I started studying my PhD, I started studying something called microelectrical mechanical systems. And these are little devices like accelerometers on your phone and everything. And they're made out of what is called monocrystalline silicon. Okay. So one of the way these things work is with elasticity. Okay. And elasticity is described with tensors. And some of my background research on how to make these little systems, and I was working at a government lab when I was doing my research and everything, I did some background research on how do elasticity tensors work, elastic stuff. Didn't really know anything about ether, or any of these other theories or anything, but what was interesting was that general relativity had tensors also. And when I tried to find out what was a good definition of a tensor and everything, you get a lot of vague answers and everything. But then I found the cosmological constant problem while I was studying gravitational tensors. And that's when I started having a problem with how you had this constant integration. And then I realized a tensor is nothing more than a measure of change of some kind. That's what a tensor is. It doesn't matter. You can call it a length. You can call it a change of something else and everything. So they had this concept of tensors and everything, and elasticity. And elasticity tensors, you can have a strain tensor, which is just a change of the strain, which would say. But in general relativity, you can have what they call the energy momentum tensor and everything. They have the strain tensor of energy and everything. So they have similar concepts. And I'm like, well, how do you have a constant integration when you have these concepts of tensors? And that's when I knew what elasticity was. So it kind of naturally carried over. I'm like, well, how do you know that the space-time is not an elastic medium? And when I started digging back further and I started looking at what Lorentz said and all these other people and stuff, once I started realizing segment magnitude, I'm like, all Lorentz ever did was use flat infinitesimals. When he uses his dx and dt, these are the same ones Newton did. If I take a line and I divide it in half, and I divide those in halves, and I divide those in half, all of my segments are the same magnitude. At no time, whenever Newton or Leibniz developed the calculus, when they were dividing lines up and they were creating all this understanding calculus, they always divided lines into equal segments, infinitesimally to an infinity of time. If you look at the concept of a limit, you're dividing things in halves and everything. So the concept of a limit does not include the concept of the infinitesimals having different magnitude within the line. and I know how elasticity works, and the magnitudes of the infinitesimals wouldn't necessarily be the same. So this is where my ideas started rolling, and I started worrying about how you would have a constant integration. I don't know if that helps.
Okay, that was a very long answer to my question.
Sorry.
I
Sorry.
got more questions. I got more questions. So you're not aware of what's called Lebesgue integration, and you probably don't know much about what in mathematics they call the real analysis, which is a sort of more advanced form of calculus. Would I be correct in saying that? You don't know what Lebesgue integration
I've studied Lebesgue integrals, and I've studied all the other ones where you take different sizes and stuff, and you do that. The problem is if your background is still flat, those integrals don't make a difference. That's the problem.
Okay, I understand what you're talking about. I just wanted to get some kind of idea. Now, when you use this term cardinality, that kind of, I'm not, the problem I have is I'm not really sure I understand what you mean by cardinality.
It simply means the number of something.
Okay, so
is it opposed to ordinality?
Yes, ordinality is the order, of something. They call it set theory. So in set theory, like when we talk about sets and everything, we talk about the cardinality of a set, the ordinality and stuff like that. If you look at my paper, I have the definition for what they were calling, the Archimedean axiom. And within the modern mathematical notation, there's nothing in there about how I can make my cardinality. They can change cardinality, but they have nothing in there that talks about how to change the magnitude of the infinitesimals. That's not included in mathematical notation, at least the ones that were given in the books I found.
Are you familiar with basis and coordinates in linear algebra and that sort of thing? You're familiar with that concept?
Mm-hmm.
Okay, just checking. I think the issue with relativity in this is that they don't really take into account standards of measure. What you're talking about is when you talk about infinitesimals being different, that means that there's a standard of measure is different as far as what physics says. So everything in physics is actually relative to a standard, like there's a standard meter stick, there's a standard but in general relativity, what they did is the standard of measure is the speed of light. Okay. And that is invariant. So that means if you believe in relativity, if the speed of light is constant, then space and time have to change.
Right.
Okay. And that's forced on you by the fact that the meter stick or the standard that they're measuring in general relativity is the speed of light. So general relativity, special relativity, the measuring stick is the speed of light. It's not space, distance in space, or duration and time. Those things have to change in order for the speed of light to be a constant.
Right. I agree exactly.
Okay.
So the issue is, are they really changing? And what does it mean to say those things are changing? So the question could be basically very simple. Maybe using the speed of light as a measuring stick is just an erroneous way to do things in physics.
I would agree with that. I think that if you look at dx over dt, and we're considering this to be constant, like we're calling it the speed of light and everything, you are right that we have this ratio of homogeneous infinitesimals, it's magnitude over magnitude, and we're saying this is going to be our constant, and we're going to change everything else around it to fit. To me, it's no different than what I showed you about the proportionality, where we had segment magnitude over segment magnitude. To me, they are making a philosophical blunder by saying this. To me, it's not the speed of light, it's the flex rate of the medium. And I think that the flex rate of the medium changes based on, where you're at, like in a gravitational field, what you would consider one. But, if time actually does contract and space also contracts at the same time, it would look like the speed of light is constant. And I can understand philosophically where it comes from, but I think it's gonna end up being a flawed view.
So in your view,
fundamental, Harry.
In your view, time isn't really changing.
The standard measurement is the metric tensor.
The standard of measurement is the metric tensor, right? And if you want to send it back, I'm saying the metric tensor is nothing more than cardinality. Is what I'm saying. I'm saying the metric tensor is wrong, and it is actually cardinality times. And when you say that you're setting your coordinate system, and then you're differentiating your metric and everything. What you're doing is you're saying, well, I'm setting the magnitude of my elements, and then I'm finding the change in the cardinality. We're saying the same things, but I believe the flawed view of it is insisting that the magnitudes are a coordinate system, a spatial coordinate, like time and space. I think that because we did not derive all this from first principles is where the flaw lies.
So anything else at this stage, Harry, you'd like to?
Well, the point I think is that in general relativity, when they say space changes, what they mean is that when I do a measurement of the speed of light, because the environment of space has changed, it makes space look like it's curved. I think that's what that means. I think that would be your interpretation. The interpretation is that time is different really means that because the speed of light is changed by the environment in which it's moving, the mass that's nearby and that sort of thing, that makes it look like time has changed, okay, because the infinitesimals that are used to make in this calculus are not consistently the same. Is that what you're saying? I think.
Yeah, that is a pretty good.
So you're saying.
Sorry, is there a delay?
I think
okay, I'm done. Go ahead. Let somebody else talk. Oh, just a reminder, we are going to talk tomorrow at 10. And I guess it's been agreed that I'm going to be talking about cosmology next Saturday instead of Roger.
And some of these things will no doubt be reverted to, which is good. So you've spurred on a lot of ideas, Jeff.
Good.
Thank you very much, Harry.
Thank you, Harry.
Now, I was actually going to send a message, but I'll say it out now. So there are a number of people in the green room. Dennis Allen seems to have audio access, but there's no camera there. So I don't know if he's around. And if you can hear me, Denny, you might see whether you can got the camera. Is there anybody else who wants to speak now before I sort of go through the green room sequentially? Okay, well, I think what I might do actually, since Jim Keane has been very prolific in posting a lot of comments about discreteness and continuity and binary mechanics and all the rest. With your permission, I've just added you to the stage, Jim. So if you'd like to give us maybe a brief your take on what Jeff has been saying and positive and negative and so on.
Well, I thanks, Jeff, for the presentation. Why do we need heterogeneous infinitesimals at all in physics?
We don't.
Oh, okay. So you're sort of you may not be familiar with my work in binary mechanics, but as far as I can see, you're a binary mechanics guy. So I guess that answers that question. Let me just quickly see if I got any more here. Oh yeah, don't pay the $900.
They already sent it back, and they said they wouldn't do it.
See that.
Let them publish your paper, and then report their invoices as a scam to PayPal.
Oh, is that what they did to you?
Well, I had to pay paper that I was asked to submit a paper to a particular journal on my light speed derivation, which I did, and there was no indication of any payment would be involved, because if I'm providing content, if anything, you pay me, not the other way around.
Right.
Okay. At any rate, they published the paper, and but I just reported their invoices as a scam to PayPal, and I've stopped receiving their reminders that I haven't paid it.
I gotcha.
Because I could bill them too, and
Yeah.
then you could accuse me of making a scam because I didn't tell you up front that in order to publish my paper, you had to pay me. And if I don't say that up front, but then later I send you an invoice, that's a scam. That's a fraud.
Right. This was a little different situation. This was a major journal with some like Nobel laureates on the editorial board, and they were coupled with this service that if you wanted to, and they told you up front how much it would cost, that they would do the proofreading and editing and stuff. And I wrote my paper in LaTeX, and I was hoping they would have somebody that could write LaTeX also. But that's when they went through it and go, we have nobody that can edit this, and they gave me my money back. So they at least they were,
okay. Well, that's honest. If they told you the financial terms up front and you
right.
agreed to that, then that's then I don't think the concept of anything sinister would apply there. I just might add that your conclusion about the importance of deriving the physical constants, the so-called fundamental constants like speed of light, electron mass, Planck's constant, etc. I've done that based upon a homogeneous segment length, which I call the primary length constant. And that might be of interest, but
is this part of the binary mechanics?
I don't.
You're breaking up a bit,
I don't think
Jim,
it's appropriate.
I'm sure Jeff.
To be that as an objective. I thought as
might
I see the
usefully look
little
at some of the
circles
material you
where
have.
the. Oh, okay. Now I'm back. Did you hear everything I said there?
Not everything, no.
Because the little circles came up where the screen blacks out.
You were breaking up. We only heard a bit of it.
We can hear you. Your picture just paused a little bit. Yeah.
Well, I was just saying that your conclusion about the objective of deriving the so-called fundamental constants based upon the concepts that you were presenting, or as a follow-up to that I have done that, and so far no one has lodged in any critique or complaint about that. And so that might be of interest to you. It's binary mechanics. You can just Google that and find.
Well, if you're using homogeneous infinitesimals, I would be interested in that. I might go over that the next few months and everything, try to see what you've done and everything. Maybe you'll give me some ideas on what to do too.
Well, I call it full quantization. And
okay.
and your work so far, which I think you've done some splendid research, and I have to give you a great deal of credit for that. But I might point out that you focused on space or a length value, and we also have energy and time as possible quantifiable items. And my work involves full quantization of all three of those.
Okay, I guess when I say length and magnitudes, I don't necessarily mean spatial length. That's one of the distinctions. The problem is that it's confusing to use lengths as spatial lengths. Lengths can mean many philosophically many things.
Wonderful. That's good.
Anything
just
else?
to the last question, because there are probably others that want to chime in. So would it be fair to say that you have rejected the theory that space and time are continuous, that in fact you're really into quantizing things?
Well, what I would say is that I reject just basically on geometry of what's called a 3-volume or just a voluminal homogeneous infinitesimal. They are not on the same footing. I know it's very tempting to treat space and time as a coordinate system and to do coordinate transforms, but that puts them on an equal footing. And our universe is 3-dimensional, not 4. And I can see geometrically why it's tempting, but I believe that that is philosophically viewed, and I believe that the geometry won't support it either. So I think that it will be challenged.
Okay, well, thank you for your comments, sir.
Well, thank you very much, Jim.
What would be challenged, the continuity or the discrete?
I think the universe is continuous in three directions, but I do not believe that our concept, I believe that time is actually going to be found out to be a process rate. And that we're using the line to measure the change in the process rate. So I think that if, like, my analogy for special relativity is, I know special relativity says that, you can't detect, there's no experiment you can detect in a moving spaceship. And my understanding, because time is fundamental to space-time, is the way that they look at it. My understanding would be is that if, let's just say I had 6 clocks, 3 clocks of one type and 3 clocks of another, and they're different types, but we've been in some kind of inertial reference frame, and we've calibrated them across all 6, and they all tick at the same rate. And let's just say that we do a boost and we're going at a faster rate. Special relativity says all 6 clocks will still tick at the same rate. The way I view this theory is that 3 of the clocks would show time dilation, but so would the other 3, but that time dilation will not be the same between them. So I believe you'd be able to detect a frame because the clock rates would start ticking at different rates. These 3 would be the same, and these 3 are the same, but they would not be equal between the 3, between the one set versus the other. That's my view at the moment.
And thank you, Jim, very much for concluding there and raising those points for Jeff to make. Now, Dennis Allen has raised something about the speed of gravity, and I've been sort of signaling him. His camera's not on, but you seem to have audio. So, Denny, would you like to say something briefly about that? No, we've no audio. I got your comments. Okay. Well,
binary mechanics says that all electrons have the same mass, but Eric Ryder's experiments lend out to that. It looks like the electron mass is a mean of a distribution. I don't know if that's a comment or is there a question?
You're looking at the general comments now.
Oh, I'm sorry. Yeah. Private chat.
That's fine. That's fine. Because there was one here I was going to impose upon you just as Jim was finishing. I'm not quite sure what he's talking about. What is your opinion of the Kaluza-Klein with relation to your concept?
I am not an expert on the Kaluza-Klein, and I have not looked at it, so I wouldn't want to comment on it because I would sound like a moron.
Okay. So, well, if Michael wants to give us his own take on that, we'd be happy to receive it. Okay. Now, so we have Nick and Vladimir. Anybody? Vladimir, if you could be as brief as possible, we'd like to hear your take on this, because Vladimir has developed this WUM theory, and it seems to be all embracing and so on. And I'd like to see what your response is to Jeff's ideas and his whole mode of operation from this very theoretical basic concept.
First of all, Jeff, thank you so much for great presentation. I was waiting for this presentation. I will tell you why. About 1 year ago, Nick, he gave me some reference on your work, and immediately I told me, recommend Jeff to have a presentation for us because it's a very important for classical physics. First of all, I want to tell you, I'm not a mathematician, I am a physicist, but physics is totally different from quantum physics. I mean classical physics. Mm-hmm. All these electrons, all the other particles, we don't know anything about them. And to have our classical approach to quantum objects, to quantum physics, it's absolutely wrong. Many times I told in my presentation, there is a very solid body between classical physics and quantum physics. What I heard today about, it's a very important for classical physics, because classical physics, it is not quantum objects, it's ensembles of quantum objects, ensembles. And all the parameters, by the way, we are 3D objects, we are classical objects ourselves, don't forget it. And what is important, when you're talking about ensembles, you don't have such energy, mass, and all this definition even. Right. We have only energy density, mass energy, charge density for ensembles of particles. What does it mean? You cannot go to the size 0 or close to 0. You cannot go with your magnitude as small as we want from mathematical point of view. It's absolutely wrong. I calculated even so named some minimum, or maybe it's absolute unit of size based on physical experiments. It's not my imagination, it's a calculations. And it turned out that the minimum size, the absolute unit of size for classical physics is 10 to the minus 14 meters. You cannot go lower with less numbers and so on and so on. That's why you cannot use your calculus, standard calculus, for classical physics. Of course, it should be totally changed language of description of classical physics. That's why I do like your approach. I do like this. It's not mathematical. It's close to physical language because we are physicists. We cannot go with 0 or infinity. I don't understand all these numbers, all these even notions. What does it mean? I'm a physicist. And physics is always something comparing with something. That's why, it's ensembles of particles. It's some minimum size of objects. You can talk about it because then you can introduce these numbers: charge density, energy density, and all this stuff. Maxwell equations, they're based only on densities. There are no charge. We invented charge. We invented a lot of different notions for elementary particles, but it's our invention. We prescribe some definitions to some particles. We know nothing about them because we have no chance even to talk about them. That's why we can talk about all something in common for all of them. Many times I talked about the temperature. Temperature of our room is some average kinetic energy of particles. I don't know what kind of particles. I know only that there is a description of the statistical analysis of the ensemble of particles, and there is some calculated value, energy density, kinetic is average energy for particles. I named it temperature. Simple like this. That's why, it's a very, very important step. You must insist on your approach for classical physics. I have no idea for string theory. I don't believe in it. I don't believe in special relativity and general relativity because they're mathematical equations. There is a principal difference between physics and mathematics. If you're going to with mathematics, it's one story. Can give some different definitions. But for classical physics, it should be only your approach, only your calculations, all your definitions.
Okay,
Then
Vladimir.
yes.
Vladimir, we're really running out of time. I think we've got your basic concept. Thank you very, very
Okay,
much.
thank you so much because I'm very excited about this
Yeah, we'll talk about it
presentation,
further.
and it's a very good addition to my approach to classical physics. I
Thank you.
told you many times about this.
Thank you.
But Jeff, he was not part of our presentation. Please come tomorrow and we will talk. We will continue our talk about your approach.
I will
Thank you so
try.
much.
I have to travel a lot. I got to fly tomorrow. But I just want to say that I don't disagree with anything you say. And you're right about classical stuff. So my view is that the limitations on general relativity thing is simply due to the limitations on cardinality and this magnitude kind of concept. But we have our universe, quantum mechanics doesn't seem to be able to be described by that. So that language may not be good enough for that. And, we have, energy levels, we have all types of discrete quanta and everything at the subatomic level. And our problem isn't what nature's doing. Our problem is how do we describe it? So I don't think that, but I think there is going to be a way to describe where the crossover happens. And it's not a problem with nature. It's a problem with our language of how we describe it. So that'll be something I'll try to work on in the future, but I don't disagree with you. Thank you.
Dennis Allen has replied actually to say that he has no audio at all. So perhaps I'll just put to you, if I may, his comment. He says, GRT asserts that gravity propagates with velocity c, but that's wrong. What would be your response to that, Jeff?
I don't know enough about gravity, but I do know, I mean, not gravity, but maybe that's true, but about gravitational waves. But my view of it, philosophically, is that there is a propagation rate that varies in the what I would call the medium. So my view at the moment is that maybe they are not the same, because if there's a physical difference between a wave such as a photon and gravity, that they may not propagate at the same rate. I don't know enough about gravity waves to say that. From what I know of what the equations say right there, I don't see any reason why they would go differently. But maybe as I learn more, I don't know.
Indeed, Jeff, but there are gravity waves, let's say, which perhaps might propagate at a similar, if not exactly the same, speed. But if you look at gravitational interaction, perhaps that is millions and millions and millions and billions of times the speed of light, because it appears to be instantaneous. I don't know if you looked at it.
I didn't. I thought the LIGO detector detected that it wasn't, but I don't know enough about it to have an opinion on it. But you're saying they were able to detect a wave that went that much faster than the speed of light?
Well, I'm even dismissing their stuff, because if you take it less than the speed of light or 3% greater than the speed of light, those are gravitational waves. Waves caused by a variation in the gravitational field, and perhaps they're propagated in an ether, and maybe they are the same as the speed of light. But I'm talking about the establishment of a gravitational field, and the fact perhaps that there's no apparent gravitational aberration, just as there is light aberration between, say, the sun and ourselves. And if there were like an 8-minute delay in the propagation of this interaction, well, then the planetary orbits would be unstable and everything would spiral out.
I see what you're saying. You're saying that the changes in the gravitational field, if they were as slow as the speed of light would be, then the orbits would not be stable.
That's it.
Okay. I hadn't considered that.
Okay. Well, thanks for discussing it. Even we may come back to it. We only have time maybe for one or two further interventions, and there's Nick. So Nick, as I said at the beginning, did provide us with the signal service of introducing you, Jeff, to us in these particular contexts of giving an updated talk. So, Nick, I've added you to the stage, and we'd like to get your response, good, bad, or indifferent, or any questions.
I thought it was a great presentation. Really enjoyed it. And so I thank you. I also thank Ian for getting around the obstacles so we could get the presentation out today, as I think it will stimulate a lot of good thinking from a different point of view. I'll just make one or two really quick points that I probably made before. I think that this is quite relevant to general relativity, but for special relativity, it has a much more fundamental flaw. So it's not really that applicable to special relativity. Special relativity is observer-centric. And as Einstein said at one point, all observers' views are equally valid, even though they differ as to what's going on physically. It seems to me that in general relativity, the basic gravitational field equations are non-relativistic, because it depends upon a specific frame. Like if you were looking at the solar system to describe what's happening physically or gravitationally, it's got to be the sun, the mass of the sun that's causing the effects. You can't pick any other observer at some other point and say his view would be equally accurate, or his frame's view would be equally accurate. So there, I think you really hit upon a great point, a great change, because you're not really requiring space-time curvature. Actually, you're saying there are other ways of viewing it.
Other ways of viewing it.
Yeah, so that's great. Thank you very much.
And thank you very much for those comments. We wanted your feedback, Nick, and so I take those as very positive, actually, Jeff. So thank you very much for that. We might have time for one more intervention. I see Cornelis doesn't have a camera on at the moment, but yeah, he always switches it on when I say that. But his mic is mute, actually. Cornelis, we have just about 2 minutes left. Just a very brief response, because we always value your analysis. But please, it must be brief.
Can you hear me okay then?
Yes.
Okay, I put my comments basically in the chat while Jeff was talking there. And my main comment was about the concept of the perfect fluid being the ether. And I see that the difficulty of the perfect fluid is that it doesn't, as far as I know, propagate strain or tension. And I think that there's a lot lost there, and that the perfect fluid would also not then propagate transverse waves, and those are obviously evident. So what would Jeff think of, has he given a lot of thought to the concept of whether the ether is analogous to a perfect fluid versus I see it as a perfect tensionable or elastic solid, like a continuous bond material, non-particular type thing. But it's basically the same concept.
Right. And I guess it didn't come across my presentation is that the words that General Relativity uses, right, is perfect fluid. And I'm just saying, I was pointing out the hypocrisy of making the planets and everything a perfect fluid, and then trying to put a perfect fluid on outer space for what the Dark Energy Task Force says they're trying to do. But I agree with you that it's not a perfect fluid, it's an elastic medium. So my first choice would be an elastic medium, an unstrained elastic medium if there's no matter or energy in it, and that the presence of waves in it is what is straining the elastic medium. And, there's maybe some limitations to the analogy, but that is how I view it.
Yeah, well, when looking at
a million miles away, maybe from your ideas, Cornelis.
Yeah, looking at the characteristics of tension in a medium and elastic waves, they have a self-focusing tendency because of elasticity. As you stretch them beyond their strain limit, the waves would slow down, and that would have a natural tendency for the wave to focus to a point because the slowness would actually make it curve towards a point. It has more of a tendency to be allowed to make a point source, a focal point of energy, which would be our particles that we see. Whereas I don't see that natural tendency to focus in a fluid.
Right. I would agree. When I say a fluid, I don't mean like a fluid like water. And I don't think that's the way that a lot of people, when they talk about it in relativity, when they say perfect fluids, I think that they say those words, but they're actually meaning an elastic medium. But I think it's more like an elastic medium.
Okay.
I think, yeah.
Okay, so we agree. I mean, we're looking at that basically same way. But I like your talk very much. Thank you.
Well, thank you for those comments as well, Cornelis. So, unfortunately, time has run out, but that is an indication of how important the talk was and how much the response was. Very positive. We've had to leave some of the comments out, indeed. So, all that remains really, Jeff, is for me to give you an opportunity, maybe a minute or two max. Just if you want to say anything else, summarize, positive or negative, your experience today, and maybe what we might do in the future. And then I'll come back and I'll officially close the meeting.
Okay.
So I'll give you the floor for a couple of minutes again.
I guess, not about my research, but I do want to thank Nick and Ian for doing this. I think what we're doing here is very important, even if we don't agree with each other's ideas. Maybe sometime we'll come to a consensus on a better idea. We can see that the think tanks of the world and the science and everything, there are certain things you're allowed to study and certain things you're not, even though things are not working out. So, you got to be able to have some dissension and some skepticism out there. And I believe what we're doing here is important. And I thank all of you for your time. Listen to me babble on. And I do hope that maybe something in here sparked an interest about learning about maybe Eutychus and learning about theory of proportions, all these other things. maybe you don't like what I'm doing, but maybe there's something in there will help you out too. So I would appreciate any feedback too on my email. It was on the video, on the slides. I can make the slides available to anybody that wants them. Just send me an email, and I will take care of that. Thank you very much, Ian.
Well, thank you very much, Jeff. That is all I really have now a pleasant duty to report that we've had a most interesting lecture, and you've actually gone back, you know, over 2,000 years past Archimedes and maybe beyond to look at the genesis of some of these very fundamental ideas that you've been applying to, you know, the analysis of phenomena connected with the universe and space and so on, and applying that to physical theories. And I think actually you've made a very good start in looking fundamentally, because you must get the fundamentals right. So I think there's a lot more that we, particularly in the CNPS, would be interested in seeing how you apply these principles in more detail, maybe to some of the hard experiments that have been done that perhaps are interpreted by the general orthodox view as supporting things like SRT and GRT, and maybe are questioned by others. So we look forward to that. And it's very handsome of you actually to offer all our participants, you know, we have a lot of participants in the social media as well as the green room, the opportunity of you know, interrogating your brains. They could send a few emails to you, and if there are problems in communications, we'll always help in that regard. And I hope to get to experience further participation by you, perhaps in the cosmology sessions, or maybe these other sessions. We were talking also about having a record of this. We do actually have a record of it, and I thank you very much for your flexibility in regard to giving a public presentation now based on past work, and also maybe slightly stuff that you're about to publish. And thank you for being flexible in that. We have a permanent record of it, which is invaluable to the scientific community, both mainstream and dissident. So I must close the meeting now, and wherever you are, I'll wish you all a very good day.